Hi everyone, welcome back to group problem 2, return of the group problem. So what do we have here? Well, we have rigid bar BCD, which is that L-shaped bar. It's supported by a pin at C and by aluminum rod 1. Now we have a concentrated load, P, that's applied to the lower end of aluminum rod 2, down there at the bottom. And it's attached to the rigid bar right at the end of the L. The cross-sectional area of each rod is 0.2 inches squared, and the elastic modulus of the aluminum material is 10,000 KSI. After the load is applied, the strain in rod 1 is measured as 900 microstrains. So what do they want you to find? Well, they want you to find the magnitude of the load at the end of the second aluminum rod, as well as the total deflection of the bottommost point of that second aluminum rod. So take your time, see if you can do it on your own, and then come back here and check and see how you did. So 3, 2, 1. Well, you paused, you're back, you did amazingly, and now you're going to check your work. So let's look at it. Okay, so first off, that strain that's measured in that first rod is due to the internal force within the member. We can calculate that using Hooke's law. So we know what the modulus elasticity is. It's 10,000 KSI. And we also know what the strain was, 900 microstrains. So that comes out to be a stress of 9 KSI. And that's the force in rod 1 is going to be 1.8 kips. Now let's look at the equilibrium of the rigid bar and try to figure out what that load P would have to be. So if we look at it right here, take a moment about point C so we get rid of those reaction forces. We have 1.8 kips right here, force 1, that's 20 inches up. And we also have force 2, which is 30 inches away, pulling down. And if you're thinking about it, well, force 2, since I cut it, it's going to be the same as P. So P would have to be 1.2 kips. Okay, so we know what the load is at that point. Now, from the measured strain, the elongation of rod 1 is going to be, well, we have our nice little equation here for strain and elongation. It'll be 900 microstrains times 50 inches, comes out to be 0.045 inches. Now let's look at that. If the top moves over, we're just assuming that it's just moving straight over, even though it would be slightly angled down. Well, that would be 0.045 inches. If you're wondering why I'm assuming that it goes straight over, even though it would be more like, if I'm really exaggerating it, something like this, it's because this angle is absolutely tiny. And we're just saying it's 0. Okay, remember we're using the small angle approximation a lot here, and that's what we're doing at this point. Now, because this is a longer moment arm, it's going to move further down than this one moved over. So let's figure out where the deflection is at D using our known deflection at B. So we simply take it, we multiply it by that ratio. Okay, so if 20 inches moves at 0.045, then what would 30 inches do? Well, it will move it some x value. If we solve for x, well, that's going to be 0.065 or 0.0675 inches. And you're like, we're done, but we're not done because we want to figure out how far the bottom of rod E moved. And so we need to figure out the normal strain in that bar and then add it to this deflection. This caused the whole bar to move. Now, how much did the bottom of the bar stretch just because of the force on it? Now, rod 2 gets elongated by that 1.2 kip load that's pulling on it, that load P. So if we do that, the stress in rod 2 is going to be 1.2 kips divided by its area, cross-sectional area would be 0.2 inches squared, and that's going to be 6 KSI. Now the strain in rod 2 is then going to be, from Hooke's law, you know the modulus elasticity is the same as from the previous one, it's going to be 0.0006, it's very, very small, inch per inch. And then we can figure out the elongation from that. So that stress will cause it to elongate by 0.06 inches. And that will be in addition to how far it moved earlier. Oop, went too far. So it got deflected downward just by the top bar getting stretched by 0.0675 inches, and then just its particular strain moved it down 0.06 inches more. So if you really want to see what that looks like, it's this. So it got deflected downward by the first one, and then it also stretched. So this might be it beforehand, and then it gets stretched some distance extra. So 0.0675, 0.06, we add those two together, and we get 0.1275 inches down. So that is it for this. Thank you so much for paying attention. Please go back over these examples again and look at all of them, look at all the equations we used. Make sure you understand why I use them and how to use them. Appreciate you paying attention. I'll see you all soon. Have a wonderful day. Bye-bye.